Hi, Living Earth. This is going to be the second notes presentation that you watch and fill out along with me. Once again, while I am going through this presentation, you need to be over on this carrying capacity document, filling in these blanks as I go through, and then after you're done with that, you're going to submit this on Canvas. Let's get started. So we're going to be talking about the carrying capacity of any particular environment. What is carrying capacity? It is the maximum number of organisms of a particular species that an environment can support indefinitely. But to summarize that, to say that a little bit more simply, it is the maximum population size that any environment could potentially sustain. It does vary as resources change in abundance. So this graphic down here just kind of illustrates the fact that this size fishbowl can support 3 fish living in it. There's enough space for everyone. There's enough water. There's enough food potentially. But if that population size were to increase, as you see here, it would exceed that fishbowl's carrying capacity, or the number of organisms that that fishbowl could potentially support. So there's a bunch of different things that can affect population size within an environment, and they are referred to as limiting factors that restrain the growth of a population. So a limiting factor is going to restrict the population size within an environment because, as you may or may not already know, a population cannot grow indefinitely and still be a successful, healthy population. And there's a bunch of reasons for that, but to summarize them into really just 2, resources are going to become scarce, and that's going to limit your population size, and 2, wastes are going to accumulate within that population. And that's really what keeps population size down, because as population size grows, the need for food, water, shelter grows with it, and the amount of waste that that population produces in the form of whatever also accumulates. So we categorize these limiting factors in a couple of different ways. A limiting factor could be a biotic factor or an abiotic factor. And what I mean by biotic versus abiotic is that factor could be a living factor or it could be non-living. The prefix bio means life. So a living factor is going to be a biotic factor. And abiotic is going to mean non-living. So some examples of living biotic factors would be really anything that's alive. So that could be any plant or animal that's influencing the carrying capacity of its environment. That's going to be a biotic factor. Abiotic factors are factors that are not alive. So sunlight, temperature, seasons, amount of water. Water is not alive, so that counts as an abiotic factor. Anything that's not alive that influences that environment. Another way to categorize limiting factors is either as density dependent or density independent. So a density dependent factor is a factor that's going to reduce population size, but it's triggered by how dense the population is. So here we are seeing competition, we're seeing parasitism, we're seeing disease, and we're seeing predation as something that is a density dependent factor. What I mean by that is as that population grows, so let's look at this population of elephants here. Let's say there's a population of 20 elephants living happily in their territory on the savannah. Their particular environment has enough food, water, and potential shelter, whatever kind of shelter elephants would need, to support them. However, let's say that population of elephants grows to 40. Suddenly there's not enough food, there's not enough water, there's not enough shelter to go around. So now those elephants are competing for those resources. Parasitism is something that also increases when population size increases. And that's specifically because as the population grows, that population is living in closer quarters, passing along parasites, passing along diseases. So that really applies here as well. Now, predation is something else that's going to be a density dependent factor. Because let's say our population of predators increases, that's going to severely limit the population of prey species in any particular environment. Density independent factors are those that I mentioned that are not dependent on how big or small a population is. If one deer is living in the forest, a fire is going to be a danger to it, just the same as if there were 20 deer living in that forest. The fire represents the same danger. Weather, like a big storm or whatever, same thing. If it gets hot outside or too cold outside, that's going to affect a living population the exact same, no matter how big that population is. And the same with any amount of precipitation as well. How do populations change in size and composition over time? Well, really, you've got birth rate and you've got death rate. Those are pretty self-explanatory, birth rate being the number of individuals born in a time period, and death rate being the number of individuals that die within that same time period. So, for instance, for example, in the US, we have approximately 4 million births per year, and we have approximately 2.6 million deaths per year, so a year being that time period. We also have immigration and emigration. Immigration is the movement of individuals or organisms into a population, and emigration is the movement of individuals out of a population. So as you can see down here in this little graphic, these birds are emigrating. They're leaving one population and they're immigrating into another. So again, emigration is leaving, immigration is coming into. We have growth rate, which is really, to put simply, birth rate minus death rate is going to be your population's growth rate over time. Because if you have a population of 10, and then over the course of the next year, 5 individuals are born, so that would make the total individuals 15. However, 2 of those total individuals died, so you have 5 additions and 2 subtractions, so that population of 10 grew by 3 over the course of that year. How is the change over time represented? So because this is science, we like to represent numbers and data and variables and everything in graph form. So we're going to represent population change over time in one of 2 ways. We are going to either represent it in an exponential growth curve or in a logistic growth curve. So an exponential growth curve is extremely, extremely rapid growth, but that growth is unsustainable because this growth curve implies that that population growth is not constrained by the environment. And that's really, really, really rare to see in nature because, again, populations can't grow infinitely. So in any particular environment, a population may have a period of exponential growth, but once that population size reaches the amount of resources that that environment can sustain, then it's going to switch to the other type and become a logistic growth curve. But when you're looking at periods of exponential growth, it's going to produce this J-shaped curve, and that's how you're going to identify it. So if you see a growth curve and it looks like this, you should automatically know this is exponential. Now, logistic growth, on the other hand, that's much, much more common to see because logistic growth is going to be this S-shaped curve that you see here. So at the beginning, if we were to just look at this small section over here, this is referred to as the exponential phase of a logistic growth curve because if you see here, this population is growing exponentially, exponentially, exponentially in this J as it goes up, but then it hits this plateau here. It plateaus off because the resources that these organisms were relying on have started to become scarce, and then their population growth is going to start leveling off here. So that's why you get this S-shaped curve for logistic growth, because that population growth is going to slow as a population reaches its carrying capacity. So this line here, this line that's represented in this graph by K, this would be the carrying capacity for this particular ecosystem.